For centuries, our understanding of the universe was built on these very intuitive, very predictable rules. Throw a ball, it travels in an arc. Push a block, it slides. Easy, right? But around 1900, physicists started peering deeply into the atomic world, and they discovered that those comfortable rules completely fall apart. So today, we're diving into this explainer by unpacking one of the most famous experiments in physics history, one that absolutely proved reality is far, far stranger than anyone ever imagined. Let's get right into it. To really get our heads around this, I want you to picture something super mundane from your everyday life. Just an oven in your kitchen. But imagine that this oven can only jump between very specific temperatures. Like say, it can be exactly 172.1 degrees. And then, boom, it instantly jumps to 181.7 degrees. It is physically impossible for it to exist at the temperatures in between, like 173.8 degrees. I mean, if I told you your oven worked like that, you'd probably laugh at my face. It makes zero sense to our intuition, right? We just naturally expect temperature to be a smooth, sliding scale. But that sheer absurdity brilliantly illustrates this core concept of quantization. And this idea literally shattered the classical, continuous rules of our everyday world back in the early 1900s. See, in classical physics, properties are continuous, meaning they can take on any possible value. A recipe can call for any fraction of flour, or a kid grows continuously through every single possible height. But quantum physics? It introduces a bizarre reality where things are quantized. Energy and other fundamental properties can only take on specific, discrete values. It's chunky, not smooth. Okay, so to prove this weird quantum chunkiness actually exists, physicists Otto Stern and Walter Gerlach decided to measure a specific property of atoms called the magnetic moment. Now, what exactly is a magnetic moment? Well, it's basically just a measure of how much an object acts like a tiny compass needle. Since an electric current flowing in a loop produces a magnetic moment, it made perfect sense to assume that electrons orbiting inside an atom would make the whole atom behave like a microscopic magnet, like a really, really tiny compass needle.
Now, measuring the magnetic moment of a visible, everyday object, like a literal scout compass, is pretty easy. But atoms are incredibly tiny, and they're entirely invisible. So Stern and Gerlach devised this absolutely ingenious, almost sci-fi setup. They built an electric oven, cranked the heat way up, and vaporized actual silver. They then shot these invisible silver atoms out of a tiny pinhole, straight through a specially designed non-uniform magnetic field. The idea was that at the far end, the atoms would strike a glass plate and stick to it. By measuring how far the atoms were deflected from a straight line, they could measure the exact strength and direction of each atom's magnetic moment.
Before I tell you what actually happened, I want you to stop and think about what results you'd honestly expect if we lived in a continuous classical universe. Think about it. Millions of silver atoms are flying out of this oven, tumbling totally randomly. Their microscopic compass needles should be pointing in literally every conceivable direction. Some point straight up, some straight down, and countless others are pointing at every possible diagonal angle in between.
Based on those classical rules, you would absolutely expect a smooth smear of atoms everywhere on the glass plate, representing all those random angles. But instead, reality delivered a massive shock. The atoms hit in exactly two distinct spots. Half the atoms hit at a specific point up high, corresponding to a positive value we call plus mu sub b, which is essentially nature's fundamental chunk of magnetism. And the other half, they hit exactly at a point down low, negative mu sub b. There was absolutely nothing in the middle. The atomic world is fundamentally chunky. Every single time you measure the magnetic moment on that vertical axis, it takes on one of only two possible quantized values. No exceptions.
But wait, because this incredible discovery creates a massive logical contradiction. Physicists call it the conundrum of projections. You see, we can choose to measure this magnetic moment on any axis. We could tilt our magnetic field horizontally or maybe at a 45-degree angle. And every single time we measure it on any axis, we still only get one of two values, exactly plus mu sub b or exactly minus mu sub b.
Let's think about this visually for a second. If an atom's magnetic moment is like a classical arrow pointing straight up along a vertical z-axis, its projection, think of it kind of like its shadow, on that vertical axis is exactly our positive quantized value, plus mu sub b. Okay, so far, so good, that makes total sense. But here is where the classical geometry entirely breaks down. If we take that exact same upward-pointing arrow and measure its projection on a slightly tilted second axis, classical geometry basically dictates that the arrow must stretch out. The projected value on that new axis absolutely must be larger than our original plus mu sub b.
And conversely, if we tilt our measurement axis drastically, making it much steeper compared to the arrow, well, the projection it casts has to be much smaller. In a classical universe, it's just like casting a shadow on a wall. Changing the angle smoothly changes the length of the result. It's just basic geometry.
So the absolute crucial point here is that it is mathematically impossible for a single physical arrow to always measure perfectly binary values on every conceivable diagonal axis. I mean, an arrow can't be exactly 1 inch long on a vertical ruler and also exactly 1 inch long on a ruler held at a 45-degree angle. It's geometric nonsense. Yet, this is exactly what the silver atoms were doing. The entire way we visualize the universe as objects possessing fixed properties like little arrows had to be completely wrong.
To solve this mind-bending mystery, physicists had to get creative. They essentially packaged the non-uniform magnetic field into these little boxes called analyzers. These analyzers had a single input hole and 2 exit ports, a positive port and a negative port. This brilliant little tweak allowed them to channel the atoms through pipes and literally chain multiple experiences together, measuring the exact same atoms on different axes in sequence.
In one really critical experiment, they first sent atoms through a vertical analyzer. They kept only the atoms that came out of the positive port, meaning, okay, these specific atoms definitely have a vertical magnetic moment of positive mu sub b. Then, they fed those specific atoms into a second analyzer, but this one was oriented horizontally. As you might expect, half went to the positive horizontal port and half went to the negative. Finally, they took the atoms from the positive horizontal port and fed them into a third analyzer, oriented vertically once again.
Now I want you to really think about this for a second. Since the first analyzer already measured these specific atoms as vertical positive, and we haven't done a single thing to disrupt that vertical alignment, what do you think the third vertical analyzer will output? I mean, logic tells us they should all, 100% of them, come out of the positive vertical port, right? We already checked their vertical status. But shockingly, the atoms emerge completely randomly again, with a perfect 50-50 split. Half come out positive, half come out negative. It's literally as if measuring the atom on the horizontal axis completely wiped its memory of its vertical state. The entire classical idea that an atom holds both a vertical value and a horizontal value at the same time, it is completely destroyed by this experiment. The resolution to this massive paradox is a truly mind-bending concept called indeterminacy. Here's the deal. When the atom exited the horizontal analyzer, it acquired a definite value for its horizontal projection. But in doing so, it ceased to have a vertical projection entirely. Seriously, if an atom has a specific value for a horizontal axis, it literally does not possess a value for the vertical axis. Now I know our brains desperately try to find classical loopholes to explain this away. It's human nature, so it is incredibly vital to understand what indeterminacy is not. Physicists are very clear on this. It's not that the atom has some hidden vertical value we just can't see. It's not that the value is changing so rapidly we can't pin it down. And it's definitely not simply that our measurement device clumsily bumped the atom and disturbed it. No, the property is literally absent from reality. The author of our source text beautifully summarizes this by saying, an atom with a horizontal value does not have a vertical value in the exact same way that love does not have a color. Asking for the vertical magnetic moment of a horizontally defined atom is just a nonsense question to the universe. The category literally just doesn't apply. So how do we escape the logical conundrum of projections? Through probability. The universe at the atomic level entirely stops being this deterministic, predictable clockwork machine. If an atom is perfectly aligned vertically and you measure it at a slight angle, you literally cannot predict the fate of that single atom. You can only calculate the statistical odds of it going to the positive or negative port based on the angle of your measurement. The math perfectly maps a curve of probabilities depending on how far you tilt the analyzer. It's just a game of chance. So as we wrap up this explainer, I want to leave you with this provocative thought. Everything around you, from the stars in the night sky to the device you're listening to right now, is built on a foundation that completely defies common sense. How does knowing that reality is chunky, discrete, and fundamentally ruled by probability, how does that shift how you view the universe? It's wild to think about. Thanks for joining me on this journey into the quantum world. Keep questioning everything, and I'll catch you next time.